All right, I think it's time that we get started, so without further ado. My name is Patrick Barrett. I work for a local company called Exosite, which if you guys don't know about us, we're an Internet of Things like hosted platform solution. So you should go definitely check us out. And if you like Erlang and things like that, you should come work for us too, because that's apparently something I'm supposed to say. So this talk is going to be about the constrained application protocol. Who here knows anything about it whatsoever? Okay. Who here is an embedded developer, like you do actual code on devices? A couple of them. Okay. So my talk's going to be more keyed towards that, so you guys might be bored, but I'm going to keep going anyway. I kind of want to start this talk by just kind of going over everything, because I think maybe some people don't understand some of the lower level stuff, and I did put a mention in there of you should understand TCP UDP kind of stuff, but I needed more time in my slides, so we're going to talk a lot about that. So before we actually get into the meat of the presentation, oh, actually I should say, you guys can say anything at any time, just shout, call me names, whatever you want to do. So just if you have a question, say it. Don't feel like you need to wait or wait for the end or anything like that. Before we get into it, I want to just kind of we're going to do terms and explain some first stuff. So for things on the internet, which I think a requirement for the Internet of Things is they should be on the internet, which people actually argue with me against that. It's kind of interesting. But at the lowest level for Internet of Things, that we have the Internet Protocol, IPv4, IPv6, that whole mess that people keep refusing to acknowledge as a mess. And then we have two protocols that we're going to talk about on top of that, the Transmission Control Protocol and the User Datagram Protocol. So the Internet Protocol, what is it? Well, basically it's the foundation of the internet. Everything that's on the internet runs over IP. It introduced this idea of what's called a packet switched network. So before the internet, we had phone lines and things like that, where you would actually get a direct physical connection to someone else. When you spun the dial on a rotary telephone, it would actually move circuitry around and give you a hardwire connection to someone on the other side of the country. That was pretty inefficient. So they came up with this thing called packet switched networks, where everybody is basically connected through a bunch of other computers, and everybody has an address, and you dump something on one part of the internet, and it gets to the place with the address, hopefully. So IP addresses, that's what this is all about. And then on top of IP, we have TCP. And what this does for us is actually quite a bit of things. First, it sets up the idea of having an active connection. So whether you're an embedded device or whether it's a web browser or something like that, before you can do any communication to a server on the internet, you need to have a connection to send information over. And this is particularly important for TCP because it's what's called a stream protocol. Basically, you can think of it as a serial port, but slightly better. You don't need to worry about having individual packets of things. It's just data goes in one end and it comes out the other. Part of that is that it handles taking the big, long, potentially gigabytes worth of data and chopping it up into individual packets that it then worries about getting those packets there. And one of the other things that it helps with is when the data does get delivered to the other end, it will make sure that things get there in order. Because part of an IP network is, since it's a big mesh, packets can go different routes or they can get lost, things like that. And that means that packets can arrive there out of order. And that would probably cause a lot of problems if your HTML page came in 6 chunks that were in different orders than they left the original server. And it also guarantees that the data will be delivered. That's what they say. I mean, obviously, if you don't have an internet connection, you can't guarantee that anything's going to get anywhere. But if you have at least a somewhat reliable internet connection, it will automatically handle doing things like retries, making sure that if the connection goes down, well, you'll know about that. And then the last thing, I think, that it will guarantee for you is that the data that you send, when it arrives at the other end, every bit will be exactly the same. So there's checksums and things like that at this level. Oh, I forgot about these two. And then the other thing that I won't really talk about hardly at all in this talk is that it'll do things like flow control and congestion control. So part of the problem on the internet is if you start sending packets at a router and it gets to the point where it can't handle it, you'll get, I think it's called congestion collapse, where it starts to get overloaded and then it just kind of throws up its hands and says, oh no, I can't do anything because of all these problems, and it basically causes massive problems. And TCP handles that by doing automatic backoff and figuring out what the connection speed needs to be. And then it also does port numbers, which is basically just a little channel identifier that says, you know, this is who I am, and that way when an application registers a connection, it can say I want, you know, port 80, and I'll take everything that comes in on port 80, or my stuff is going out on 49627 or something like that. The other protocol that we're going to talk about today is UDP. It stands for the User Datagram Protocol. This is kind of a Unixy thing where it's a user protocol because it's available to a user level instead of a root level user on a system. And basically what it does is it gives you something approximating a raw IP socket, but without giving you the danger of having a raw IP socket to every user on the device. So what does UDP give us? Basically nothing that TCP gave us. The two things that remain are the port numbers, and that every bit will be exactly as it was sent, so you get the checksum and stuff like that. I had something else I wanted to say. I don't know. So you guys hopefully not too bored yet, but we're going to do more terms. Yay. The other thing I kind of want to just do at a much higher level is there's what's called a client-server or request-response architecture, and that's how the internet works. So generally, you know, the way everything has worked since the beginning of internet time is you have a server sitting somewhere on the internet, and you have a client, which can be a web browser, a device, a smartphone, or something like that. And the device is the one that initiates a connection up to a server and says, I want this thing, and then it says, thanks. So on the device, you know, something happens, ask for a resource, the server does something, sends it back, and then you do it all over again. There are problems with this that we're going to go into later when we get into actually more of the HTTP and CoAP comparison stuff. Has to do with kind of real-time kind of stuff. So, and then oh, I didn't actually explain what the other two terms were. So then the other two terms are NAT, which stands for Network Address Translation. This is something that happens at like a home router. So you guys all know IPv4, oh no, we're out of IP addresses. The way that we're solving that, quote unquote, now is something called Network Address Translation. So you have two different networks, the broader internet that has lots and lots of IP addresses, and then you have a local network where everything starts with 192.168.something.something, or 10.something. And network address translation is what allows those networks to have, you know, connections from the inside connect to the greater internet. And then a firewall, it's a firewall, totally a wall fire, promise. So for the purpose of this talk, I'm going to say that firewall is the same thing as NAT. It's totally not, but for what I'm talking about, pretend it's the same thing. Generally, what happens here is you have to have stateful connections. So, you know, you have this 10.IP address, and if I'm someone sitting on the internet somewhere and I say I want to send this packet to 10.1.2.3, it doesn't know what that is. That's not a valid network address. There could be hundreds of thousands of computers that have that IP address. So what happens with NAT is you have this internal IP address. You send out a packet. It has your source, you know, port and IP, and a destination port and IP. And it'll actually rewrite the source IP address to be its own IP address and port that it chooses. And that's the reason it has to be stateful is it keeps track of those things, because when something comes back on that IP and port combination, it needs to know what computer route it to after that. So things need to stay stateful. And that includes UDP, which isn't actually a stateful protocol. So it kind of adds a little bit of a state that needs to be part of the protocol. And the reason for this is that you want, well, I shouldn't say the reason. One of the side effects of this is that, you know, computers on the internet can't just send arbitrary packets at your computer. So, you know, in the dark ages of the internet, we always had internet worms and things like that, MS Blaster, that could infect a computer just by sending a packet to it. NAT and stateful firewalls and things like that actually kind of alleviated this problem because you couldn't get a direct connection. So you couldn't have these worms that were just flooding the complete internet. I mean, they do actually still exist because there's a lot of insecure computers out there, but for the most part on personal computers and things like that, it's been a solved problem. And as I said before, the way that you do let packets come back in is if you have a matching packet that just left. So we were talking about CoAP. Well, we're not actually going to get to that yet. So let's talk about HTTP first. I'm sure pretty much everybody here, who knows what HTTP is, what the syntax kind of looks like of it? Okay, so you guys are going to be bored for the next like 2 minutes. Basically with HTTP, you have, it runs on the top of the TCP protocol so that you get a lot of that automatic retry, automatic connection, you know, you have your state in your connection. It does the checksums and all that kind of stuff at the TCP level. It's pretty much very strictly client-server based in how it works. You know, there's definitely a request and a response that's part of HTTP. And then it's a text-based protocol, which is really, really great for if you're developing a web server in the 1980s and you are trying to debug problems and you see packets flying past you and you want to know what's going on. It's great because you can just read it straight off the screen. But one of the downsides of this is that it's a pretty big protocol. You know, if you're a web developer, you may completely disagree with that because it's actually not that many. You know, it's maybe a kilobyte in a really big packet. But for something like the Internet of Things, it's actually a really, really big protocol because you're going to be making maybe a request every second or something like that. Over the course of a year, it can add up to something like 40 gigabytes, I think I calculated once. The other thing that was a big benefit to HTTP is that it's extensible, which means, you know, you can just create a header in HTTP and call it whatever you want. Sometimes people put the -x thing in front of it, even though it's not recommended anymore. But it's, you know, you can basically put on your own semantics on top of HTTP. So this is what an HTTP packet looks like. This is actually probably a really small packet if you're a web developer again. But to me, this is a massive packet. This is actually an API request to the Exosite simple data API. So we've got our path where we're saying we're going to use an alias. There's some other headers. We got the CIK, which is just like an auth token. And then what we're saying here is that we want to say that the temperature is equal to 26 right now. And the server says, okay, yep, all looks good, 200 something, and I'm not sending any information back, blah, 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 blah. So I'm going to make that look a little worse now. So we're just, because why not? So, you know, it's basically, there's a lot of bytes going on there. But, you know, that's the same packet here. But here we can use CoAP and make that look better. Yay. So this is actually the exact same information being transmitted. That we're doing the exact same operation to the CoAP API of Exosite, but we're using dramatically fewer number of bytes here. But I don't know about you, but I can't really tell exactly what's going on there. You know, oh, I reordered those. Damn. Okay. So CoAP is a protocol from the IETF, the Internet Engineering Task Force, who they're the same people that made, you know, IP, TCP, UDP, and HTTP. They run all the, you know, if you see something that's called an RFC and then a number, that's going to be something probably from the IETF if it's related to the internet. So there's a whole bunch of text up there. You know, this is the actual introduction from the RFC itself. But basically the things that you kind of want to look at, you know, low power lossy networks, 8-bit microcontrollers, tens of kilobits per second is the data rate that we're probably going to be going with. There's something about like 6-LoWPAN. It's designed to be easily interfaced with HTTP, blah, blah, blah. So what is that actually saying and why do you care? So the first thing is that they designed it very specifically to be like HTTP. One of their goals was so that people who understood HTTP could come in and just kind of hit the ground running and understand the same kind of semantics that are there. But it's a little bit different. The first thing is that it uses UDP. This actually lets us do a couple of really fun little features that you're going to see in a demo later. Because we don't have that stateful connection and we can have packets flying every which direction at the same time and it doesn't really matter. It is also a client-server protocol, but it's more than that. So we'll see those fun things later. It does request response in the same way that HTTP does, but again, it does more than that. The big thing, or one of the big things I should say, is that it's a binary protocol. So it's much, much smaller, as you saw earlier, but that can be unfortunate for some things like debugging. But one of the big things that making a binary protocol let them do is they made it really, really easy to parse. So if you have something like an 8-bit microcontroller, something that is so small you can almost barely see it, that will have enough power to do a CoAP type communication with a server over the internet. There are parsers that have been written for this that implement most of the protocol that are less than like 500 bytes of code space. So it's a really, really, really small protocol. It's also a very, very well-defined protocol. So if any of you guys have ever tried to write an HTTP parser, you might know that it's not the most straightforward thing in the world. There are a lot of things that are kind of undefined in it. They fixed a lot of those problems with a bunch of new RFCs that they're still working on right now. I think that maybe just got released a couple months ago. That are like the 7000 series. There's like probably 10 different RFCs to redefine HTTP 1.1 so that it's more strictly defined. But CoAP, they got it right from the first time. They knew that was a problem. And then it's also extensible again. So like HTTP, it has the kind of the idea of headers, but they're slightly different, and it's a little bit more of a pain in the ass to use, which I'll get to in a second. This is the actual format of what a CoAP packet is. So we've got a version header, which is like the HTTP 1.1 string in HTTP. That T is a type. So there's 4 different types of packets that you can have in CoAP. There's confirmable, non-confirmable, reset, and acknowledge. So reset is anytime there's some error, acknowledge is acknowledged, and then confirmable is any request that you make that you want a response on, and non-confirmable is any request you make that you don't care if you get a response or not. And then we have this TKL thing, which is the token line that I'll get to in a second. We have a code, which is actually both the HTTP verb and the HTTP status code. It does double duty there. So it has the 4 verbs that CoAP has right now are stolen from HTTP. There's get, post, put, and delete, which are the first 4 numbers. There's also an empty, which is no verb at all, which is only used for resets. There's a message ID. So since we don't have TCP to do all of the things to do retries and deduplicate packets and things like that, it's put into the protocol here. So it's just a 2-byte number that you can use to kind of, based on time and things like that, there's a certain protocol for how you increment the message ID. And then you have the token, which is kind of the same thing, but kind of in a no man's land, and nobody's really sure what it does, even though the protocol is brand new. People have differing opinions on what it's for, but it's basically the same kind of thing where if you send out a packet and you're expecting one back, it's supposed to have the same token, which the idea is so that people can't just send you an arbitrary packet and say, hey, look, this is something that you just probably sent. But you shouldn't have that problem because you should be using DTLS, all of you. Security, good thing. And then after that, we have the options, which is our headers. All of these are what's called tag length value. So you have a code at the beginning that is a number that represents what header it is, and then there's another number that is the length of it, and then the value. So that's part of the whole easy to parse thing. You don't need to go through the string and find the new line character, and you don't have to worry about any of the character encoding of things. It can just be arbitrary binary data. It doesn't care. The same goes for the payload. It can be arbitrary binary data. The 111 thing is just a payload marker that says payload starts here, end of options kind of thing. And then the length of the payload is just the length of the UDP packet minus the length of the header stuff before that. So it's pretty simple. So again, we can kind of keep looking at that and say, oh, I think that one, let's see, 40. I think that was confirmable. Okay, yeah, so that's a confirmable type packet, but that's not the most efficient way to try to debug things. So I'm going to invent my own format for what CoAP looks like to a human, and it's that. So it's basically just a bunch of JSON for all the different parameters that's in there. So you can see that this one in particular is doing a post to the URL /1a/temp, and we have a query string that is the CIK in this case, which we're just using that. We're abusing that parameter right now because we don't have our own header. So part of the problem with CoAP is that all of the option numbers, they're numbers. So you can't just make one up because what if someone else chooses 37 and you chose 37? So there's actually an IANA register that lists out what all of them mean. And you basically contact them and say, I want this, and they say, okay, after some going back and forth. And then you have your own option number that's a header. And we haven't done that yet, so we're using a query string, which violates the protocol when we do that in binary instead of in hex text, but whatever. And then we've got the payload here, which is 26. So this is actually, again, exactly the same thing as the first HTTP packet that we saw, where we're sending the value 26 to the temp. We're saying the temp is 26. Oh, and then it's coming back and we're getting an acknowledge. It's saying that it changed, which is kind of like a 200 response code. CoAP doesn't actually have a 200, it has a 2.05, which is kind of the same thing, but just means content. Wait, no, it changed. 2.01. And there's no body or options or anything for that. And then the message ID there is the same for the two messages. So it puts those together. And now we get to the fun part that you're probably all going to be laughing at me because it doesn't work. We're going to try and do this for real. So we've got that same request here. We're going to do a get on message instead of temp. I click that button. Yay, it actually worked the first time. So what this is actually doing a CoAP request from within my browser through a couple proxy servers, because you can't do UDP from a browser, up to the Exosite server and doing all this stuff in real time. So I can go in here and we can change this to a post. And we'll add a payload. Give that a go. Okay, it came back and said that it was changed. We'll go back to the original. And it comes back and our payload's now minibar. Yay, it worked. I'm kind of surprised. So that's cool and all. It's basically exactly the same as what we've done with HTTP. It's not really any different, except that it's a little bit smaller. But if you're on a home network connection, you maybe don't really care about that. So what's something really, really cool that we can actually do with this? I forgot to clear this. So there's a new option that I've added now to this that's called observe. And this is actually still a draft specification that they're working on. It's pretty much going to be done and published as an RFC exactly as it is. But what this allows us to do is it tells the server that we want to observe a resource on the server. And then when the server says OK, it will come back and notify us anytime that resource changes. And we'll just get an asynchronous a UDP packet sent to us. This is something that you could kind of do with TCP if you had a different protocol, but you can't do over HTTP. So let's see something really, really cool that may or may not work. So I'm going to click the button here. It's going to come back. It's going to say, OK, observe 0, which is just kind of an index number that counts. And then a content format of 0 that says it's plain text. And then there's this max age header, which is a kind of a cache thing, which I'll explain a little bit more in a minute.
Did you need to pass the message ID out when you made that request for the observe?
So part of the way I wrote this library is that if I don't have a message ID, it'll insert a random one. Just because if I click the button more than once, I don't want to have the same message ID. So now we are subscribed to that resource. And up here, I actually have a little dev board that is connected to the Wi-Fi here. And it's also using CoAP and connected to the same, using the same auth token there. And hopefully if I push this button, damn. All right, let me restart it. So what was supposed to happen is that was supposed to change to a, oh wait, maybe it did change and it's just -1 again, because I reset it. Well, let's find out again. So if I push that. Hold on. Okay. Try that again. Push the button, and it changes. That was supposed to happen the first time. So push the button, click, click, click. So That may not look that impressive to you, but I promise that it is very, very impressive, because what's actually happening here is the Exasite server that we have hosted up in AWS, we're sending a packet from that embedded device up to that system. It's processing it, sending it out to all the other subscribers, and we're getting an asynchronous notification here, all in under about 200 milliseconds. So if you tried to poll a resource on a server every 200 milliseconds, you would kill everything within a 30-mile radius. And then now what we're going to try to do is do it the other way and have that fun thing that probably won't work, which is called L. Oops. So hopefully when I push this button, the little LED right here should turn off. Well, it's not working. But that was the part that I was afraid wasn't going to actually work, so that's not that surprising. Oh, it's still a get, that's why. Let's try that again. There we go. So if you guys have, maybe you saw like the Gizmodo article a few months ago, or there's been various things where people complain about IoT, and there's the famous GIF at the top where he walks in the door and he goes like, looking up at his lights, and then like 4 seconds later his house lights turn on like one at a time, and it takes like 10 seconds for all of them to come on. This will solve that problem, hopefully. Right, yeah. Exactly. Question?
So, if I'm understanding correctly, this side
Yep.
is the light that has to have the microchip or whatever that right?
Yep.
And this side is your phone or whatever.
Yep, or even another light switch.
Yeah.
Yep.
So that's how the status of this side goes into here. Right? You observe that payload is the control to the light to turn it on or off or dim or whatever. Right?
Yep, exactly. Yeah, so just to repeat in case anyone didn't hear, he was just clarifying that you have 2 different resources. One side is like a light bulb, one side is either like a phone app, or it could be a switch, like a light switch or something too. And you have, when you observe something, it sends you requests, and the payload is what actually controls like the value of that kind of thing.
At which points in this process is CoAP being used versus HTTP or something else? It's going out over Wi-Fi and some of like the re-inspiring.
Yeah, so it's all CoAP.
Okay, so it's going over UDP then to get to AWS?
Yes, sort of. So this is actually a Reveal.js thing in HTML in the web browser. You can't do UDP from a web browser, so I wrote a WebSocket to UDP proxy that I'm proxying all this stuff through. But once it gets there, it's all CoAP stuff that's traveling over the network. There's no HTTP going on.
Where's the thing that's getting the UDP? Is it public internet facing?
Yep.
Okay. So
Yes.
you have a WebSocket to something that's out in the public internet that's receiving the UDP?
Yeah, I have a Heroku app that's just hosts a WebSocket, and it is able to send out UDP packets to a certain list of hosts that I've whitelisted. And when I just send a binary, like a plain binary WebSocket message, and it just takes whatever that is and sends it out to wherever I told it to.
Something in here is receiving that, and then you're also.
So here, let me explain that a little bit better. So we'll explain it on this end because that's easier to understand. This is using UDP straight to our server in AWS. And you could have 2 of these and have a button on each one, and it would send a UDP packet from here up to our server in AWS. It's writing to, we call it a data port, which is just a time series list of data. So, and I write the light level that I want. It does some processing. There's another client that is subscribed to that. And it knows that, and it has an active subscription with an IP address and port number associated with it. And it just says, this data port changed, and I'm going to send you a UDP packet that tells you that.
Okay. And you said before that essentially there's an established connection, and that's why the packets make it back.
So that was the whole NAT firewall thing.
Yeah.
So in UDP, there are no established connections.
So how does a UDP packet originating at AWS make it through the NAT to that device?
Yep. So I'm going to take half a step back there. and just if there were no like NAT and we didn't care about security, it would work just fine. But we have to. So the whole firewalls being stateful is what what allows this to happen. So if you think like if you're doing a Skype call with someone, you have UDP packets coming out and UDP packets coming in. So it's the act of a UDP packet from a certain port going out that tells the firewall, open a connection here. And that's the part that we're keeping state of. Yep, question?
So I guess two things. That one brings up, is there like a keep alive on those?
Yes, oh, I never talked about that. So this max age thing, so it's set to 120 seconds. After 120 seconds, and it's probably actually happened by now. Oh wait, no, I got rid of that. Our server will say, oh, I know that you have a resource that is now expired. I'm just going to send you another one. And then the thing that I'm not actually showing up here is that anytime one of those asynchronous notifications comes in, I have to send back an acknowledge packet. It's just like a 4-byte packet that says, yep, I got it, don't send me anymore. If I didn't, it would keep retrying 4 times with exponential timeout kind of thing.
So only confirmable would have that max age on the response?
No, not necessarily. Actually has more to do with what the code is. So when our status code comes back, we have like a 2.05 content, which is what we have here. And that it's just saying, yeah, it has more to do with that content because it's kind of saying whatever this resource that I'm giving you, it will expire after this amount of time.
Oh, okay, got it.
Yeah, it's valid for this amount of time, I should say.
Message expires the date it expires.
Exactly. And so part of it is like you can have CoAP proxies and things like that. And the idea is that the proxy is supposed to, find the max age, figure out when it received that, and like continue counting down so that it all filters down and all that kind of stuff.
I was asking that because in the old world we call the unreliable data.
Yeah.
So libraries generally with the confirmables are going to retry?
Yes.
Okay.
Yep. Here, I can actually show you something kind of cool. Oh, this is going to be way too small to see, isn't it? Okay, so here I have basically the exact same thing. We'll just change this so that it's something different. We're going to do an observe on that, and this is just a little checkbox that turns on whether it's going to send those acknowledge packets back. So I click do it. We're going to get that number back, and then if I push this button, we'll see it changes to 14, and then I'll just highlight that to show that it's going to change again in a second. Or maybe I broke something. Oh, I'm actually setting reset, so it's not going to retry again. But if you look here, so what is happening, this second to last line here is the notification that we got back. And normally you'd send something with an acknowledge type here. I am setting it to reset, which basically says, I got a packet that I don't know about. Don't send me anything else about that. And that is how you unsubscribe from something. It just kind of keeps stuff clean. I don't actually have a way to ignore packets right now, so I can't show you what I wanted to show you. But does that answer your question? Okay.
Another question?
Yeah.
What's which devices or microcontrollers or basically hardware pieces have implemented this protocol?
Yes. I mean, I wrote a library in C for it. So if you have a piece of hardware that can do IP, you can do this. That's basically the answer. Like I have it running on an Arduino. This is a TI CC3200 Wi-Fi thing. We have another TI Ethernet part. I've got a thing from Microchip that I'm working on right now. But basically the idea is that you can port it to anything just by using the C compiler. Yes?
So when you tell it to observe, are you polling the server or is the
No.
server pushing?
Server is pushing. So the whole idea here is that you don't need to waste data on polling. If we set that max age to something ridiculous and your router was insecure, you could have it just sit there for years at a time and it would send a UDP packet back and you would just get it. Push, no keep alives, no polling, no nothing.
But it does require the router to support whatever that max age is and keep that connection active?
Yeah, and it's kind of, you would kill yourself if you tried to do it properly kind of thing. The IETF says that the minimum is supposed to be 5 minutes, that connections just will stay alive. It's sometimes like 3 seconds, which means you can't do any kind of push notification, anything with this. Usually that's just like corporate networks and things that are like really, really locked down by someone who doesn't know what they're doing. But it happens, and I've had to debug one of those already.
So like if you're doing like a daily update, would that time out and then the packet?
Probably it would time out and the packet would get dropped. If you're doing something daily, you're probably better off just polling anyway. Sometimes it depends. I feel like I didn't fully answer some question or I had something else I wanted to say. I don't know. Any other questions? All right. So, okay. Yeah.
If you end up in a situation where the router is not behaving, it's terminating sessions with respect,
Yep.
is there some mechanism for the protocol to pick back up and communicate, or is it just kind of broken?
It depends how broken you're talking about.
Say it's set to 60 seconds because they.
Yeah, I mean, so we haven't implemented it yet, but the idea is that you can kind of do this a discovery protocol of how long your sessions last and things like that. I think that's still a draft actually, but there are ways you can do that where you just have the packets get sent every 58 seconds instead, something like that.
Will the server ever queue up? So I previously subscribed to something, and then there's a point where they start not getting received. When I receive something, I acknowledge it, right?
Yes.
So will the server, and you said that the server will retry 4 times and stand down. Are there implementations that queue those up and then reestablish?
I'm going to say sure if you want to, but I don't know of any that. I mean, the thing is that it's new protocol. There's not very many like high-level applications that are doing this yet, and that's kind of something I think would be more at that level. There's no reason you couldn't do that, but I don't know of anybody that is doing that yet. But the protocol would support it. It's kind of like if I asked you an HTTP question and said, I didn't request this once. If I request it next time, would it give me the last one or the current one?
Yeah, so I sort of think of it like a lot of times. So there's a sort of move from REST to WebSocket APIs.
Right.
But we always have to maintain a REST API. So what we do is we basically queue up the messages, and when the connection gets reestablished, we send them all.
Right.
And so I was sort of thinking in those terms.
Right, and basically you can do that. It's the same as what you're doing now. You can do it, but you don't have to. Any other questions?
So what have you been able to use so far? You mentioned you've already kind of ran problems with it along the way. So what have you built out with it?
What can I talk about? We've rolled out. I know we have one customer that's in production right now. That. How are my coworkers here? Okay, no one's gonna know. Oh wait, there's a video. That does personal fitness tracking for things with wheels, and they are using CoAP right now to send real-time data back from those athletes up to our platform for real-time monitoring for that. We actually haven't had many problems with that because they're using cellular, and as crappy as a cellular connection is, for some reason they did UDP right. I don't know. It also helps that they all have like a public IP address, so there's no like anything going on there getting in the way. Yeah. All right. So, oops, I meant allow. So I've been kind of just extolling the virtues of it here, but I want to make sure that people don't go home and think, oh my God, this is the best protocol in the world. I'm going to use it for everything that I need to do. I'm making my new web application. I want to use CoAP. No, don't do that. The big thing is that it's brand new. The RFC was just finalized in July of last year, so it's not even a year old yet. I mean, HTTP has like what 20 or 30 years since it was standardized the first time. And people understand how HTTP works and all the idiosyncrasies of that and stuff like that. But CoAP is kind of brand new, and even people don't use UDP as much as you would think. The big thing is that it's still kind of evolving. I said earlier that it's well defined. Well, the things that are defined are well defined. But like the whole observe thing is still a draft, and it probably won't change, but there's a chance it could change. There are other things like what are called block transfers. So UDP, it doesn't do any of that whole stream protocol chopping stuff up, So if you have a file that's bigger than like 500 bytes that you want to transfer over CoAP, you need to use more than one CoAP packet. And what they do is they have this thing called block transfer where you have a header that says it's, it's kind of like the range header in HTTP. It's, block X of X kind of thing. And there's a lot of stuff with like group communication and local network stuff that it's definitely still evolving, that they're still working through. To go along with the UDP thing that I said earlier, there's doing security right over UDP is difficult, mostly because there aren't that many well-supported libraries yet. Things like Siazel and like OpenSSL and things like that definitely support DTLS, which is the datagram version of TLS. But if you're going to do something on an embedded microcontroller, you're probably going to run into the fact that they just didn't bother to implement it because they didn't know what it was. What? Well, sometimes it's that, but like this device right here, there's actually 2 ARM cores in here. There's one that only does the web stuff, and they implemented everything SSL3 through TLS 1.2, but there's no DTLS. So you're going to have to do it yourself in the application side of the microcontroller. The other thing is that it's more complicated. I mean, HTTP, you have a request response. It's always that. It's something you can read out the page. Whereas with CoAP, it's something that's binary. So you need more tooling to debug this kind of stuff. I mean, you're probably going to be looking at a Wireshark dump anyway, so it doesn't matter. But sometimes, you need to get on your production server and do a TCP dump. And then you basically need to pipe that, output it into Wireshark so that you can actually read it. Or there will need to be a CoAP dump command that people start using that won't be available for the next 10 or 15 years probably, because servers don't progress very fast. Yeah. Yep. They supported like most of the drafts all the way through, and the versions for the since. So CoAP draft 18 is the same as the production one, and so they've supported it since like over a year ago, probably like a July ago or a January ago. But yeah, it has really good support. The only problem you're probably going to run into, and I don't actually know how you solve this in Wireshark, is if you have like custom options numbers that haven't been, that weren't available at the time that Wireshark version was made. There's just going to be random numbers in there that you're going to have to read through, but there probably aren't going to be that many of them. So that's all I have. If anybody has any other questions, I'm welcome or happy to answer them, or I'll be around for. When is this supposed to end with? Oh, wow, I'm like right on time. I'm impressed. All right. Well, thank you very much.
Thank you.